Alright guys, today we are going to try to answer this question for today. Why is energy quantized? So before we can understand why energy is quantized, like why electrons do what they do, we got to understand what a standing wave is. And here we have a couple pictures of a standing wave. So a standing wave, if you think about it, is like if you took a jump rope and held on one hand and like tied the other end to a wall and just shook it, right? If you go nice and slow, you'll get a wave that goes boop, 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 boop. But if you shake it really fast, you'll start getting more waves. And it sort of kind of does this thing where it's like a repeating. It just kind of goes up and down. Instead of like a wave that goes like this, where it propagates through space, it just kind of goes boop, boop, boop. Looks like it's staying still. So like if you pluck a guitar string, we see the guitar string going up and down, but what's happening is like there's a wave going back and forth because the guitar string is fixed at 2 points, at 2 nodes. So I want you to keep that in mind, and I want you to think about this. Like if you do have a standing wave, or like a guitar string that is plucked, the 2 ends are called nodes. That's where there's no movement. And I want to ask you, if this is a guitar string, could you have a node right there, like right in the middle of the guitar? The answer is no. Because that's ridiculous, right? I mean, if this is the length of the guitar string, you're not going to magically have a node right in the middle, right? Okay, I want you to keep that in mind, right? Because you can't have half of a wavelength, right? It doesn't work. You know what I mean? If we did that, if we put a node here by placing our finger on the string, we would now have a standing wave that would look like this. And if there's one here, it's a standing wave that would look like that, and so on. Do you guys get what I'm saying? But you can't have a node halfway through a wave. It simply doesn't work that way, which is, believe it or not, a lot about how electrons work. So with Bohr's model of the atom, right, it worked wonderfully, but nobody really understood why. Okay, nobody really understood why. And this guy named Bergoglio came up with it. I want you to look at that over there. See, here's what's going on. Electrons are particles, but they also have wave-like properties, which was like, what? This is like what broke people's brains. So Bohr was able to show that there were these like quantized levels, but nobody could understand why. Bergoglio, this dude was like, well, electrons must be like waves. Which, no, because electrons are particles. How can particles have wave properties? Waves are just like energy propagating through space. How can a particle be like that? Well, turns out everything has a wave property. You and I have a wave property walking across the room. The difference is that when the matter is very small or has a very, very small mass, it has a relatively like large or observable wave function or wave pattern, but the bigger something gets, the smaller that wave becomes. But we'll get to that in a minute. But here, actually, there is why energy in the universe is quantized or limited. Here we go. So let's take this like the red line here. This is going to be our orbit, right? Like the way that Bohr described it, right? So if you think about it, here's a trough of the wavelength. We go up, we go down. Here's another trough. So that means that for this particular wave, this distance right here, this is one wavelength, right? And so this path that the electron takes, because it has a wave function, has to be some multiple or some unit of that wavelength, because as one wave finishes, right, so as this wave is finishing, it has to meet up precisely where it was before. And here's why. Let's take a look down here. So if it doesn't match up perfectly, here, let me move my window down a bit. If it doesn't match up perfectly, what happens is the waves cancel out. So if this is going, so what happens here? So let's say this guy's going up, up, down, up, down, up, down, up, down. So here it's going down, and so what we end up with as it continues over here is it'll sort of like do the opposite of itself. Well, when waves do the opposite of itself, what happens is, at this point right here, we have a positive displacement and at the same time of equal magnitude and negative displacement. And if you have a wave going up and a wave going down of equal magnitude at the same point in space, the waves cancel each other out and the wave disappears. Like you don't see it anymore. We have no displacement, so we can't observe it. which would mean the electron would disappear. Nope. So, but this is also very similar to having a guitar string. As it's going up and down, you can't have a node, like, right? You can't have a node like this. This would be a good node, right there. That would be a node. You can't have a node in the middle of the wave. The wave would cancel. It would fail. Like it would there's all kinds of weird interference, and it would basically stop. So, because an electron, a particle, has a wave function, that path has to overlap. Otherwise, it's going to cancel itself out. But really, the reason is because it's moving in a wave, because it's a physical object, it can't fit there. Like it won't. It'll like basically knock itself out. So what that means is that this path right here, the circumference has to be some unit of our wavelength, or the electron can't fit. It just can't. And that's it. Bam. All of a sudden, we have fixed levels where the electron can be because of its wave function, right? Because it can only possibly exist in those wave functions. And so it has to be some unit of the wavelength, which is like crazy to think about, but it's true. So this dude Broglie, his answer was that electrons are both wave and particle at the same time, which made no sense to anybody. But man, did it work. It turns out it's true. All of matter has a wave, like particles, like you and me, have wave functions. So we propagate through space with a wave function. And here's what it comes down to. So let's do some math. 2 pi r, the circumference, has to be some integer, like 1, 2, 3, 4, 5, of the wavelength. Right? Just because it has to be. I mean, that's all there is to it. And the wavelength, so this wavelength, the way that we calculate the wavelength, this wave function, is going to be, what's his name? Planck's constant times the mass of your particle divided by u, and u is going to be the velocity or the speed of your thing, and m is the mass. So let's stop and think about this for a minute. How is this possible? Like what does this mean? What is this math statement telling us? Right? It's telling us that the bigger the mass you have, the smaller this will become. So the wavelength will become smaller. Does that make sense? So that's why when we throw a baseball, we can't really observe its wavelength because it's so stinking small. Same way you and me walking down the hallway, the wavelength is so small that it's like completely unobservable. Like we're never going to be able to observe like our wavelength because our atoms and molecules have a fuzzy edge and the wavelength is smaller. It's smaller than that fuzzy edge of the electron cloud. So it's like, who cares, right? However, if the mass gets very, very teeny, gets really, really small, well, at that point, when that mass gets really, really small, this gets much larger, and so the wavelength gets much larger, right? So it gets more refined or more observable in relation to the size of the thing that we're looking at, and that is given that the speed of our particles are the same. So again, everything is all relative, Einstein. Everything is all relative to one another. You can't change all the variables at once. Do you guys get what I'm saying? And so for evidence on this, I want you to look at this thing down here. This is this is beautiful because people are like, well, prove it, buddy. Like show me how an electron has a wave particle. Well, if you look at this over here, this one down here, this is what it looks like if you take X-rays, light, waves, right? You put it through an atom. This is the pattern. This is the refraction pattern we get out of it. Look, there's like a double line. Well, if you take electrons, put it through the same atom, this is what you get over there. Like, look at that. That's crazy. They look exactly alike. You've got the same double line, the outer, and these two outer rings. But if you notice over here in the wave, this is a very solid wave. You can see the wave. That's definitely like a wave front. It's like there's no beginning, there's no end. But here, there are definite particles. Like see how it's all sort of pixelated, like dot, 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 dot. But in the same pattern as a wave. Like what? How? Evidence. I mean, it's like you can't say no to that. But there it is. Like it turns out that particles have wave functions. They sure do. But we are so big. The world that we live in is so big that we're not used to seeing it. When you shrink down to the quantized level of the universe, like particles have wave functions. Bet you didn't know that. I didn't either. And that's like makes my brain explode every time I think about it. So let's do some math here. So we're going to calculate the wavelength of two particles in these two cases. The first is a tennis ball. The fastest serve in tennis is about 150 miles, or let me move you over here. 68 meters per second. Okay, that's great. 60 meters per second. Calculate. So I'm going to write that here. And I'm going to use meters per second. That was all backwards because I was talking. Because we don't use miles per hour, but I'm telling you right now, watch out because you'll have some problems given miles per hour. Change miles per hour to meters per second. No biggie. We want to find the wavelength, right? Associated with this. Okay, and so there's the mass. Okay, great. So this is easy. The wavelength, if you remember, equals Planck's constant times, or divided by mass times speed. So, plug and chug, baby. Let's go check it out. So, Planck's constant 6.6. Hold on a second. 6.626. 6.626 e to the, is it minus 34? I'm brilliant. I'm starting to memorize. Look it up if you can't remember. Okay, the mass that we've got going on here, 6e to the 2, e to the minus 2 kilograms. That's our universal mass. And the velocity, 68 meters per second. Okay, I'm going to pause you guys here so I can do a little bit of math, and I'll be right back. All right, I got 1.6225 e to the minus 34 meters. Okay. Okay, so first of all, I want you to like clue into the order of magnitude here. Planck's constant, the smallest bit of energy possible in the universe, is at the order of magnitude of minus 34. So the wavelength of a tennis ball is to the order of magnitude of minus 34. Just to give you an idea of how small that is. Okay, so all right, that was A. So let's crank into B. Oops, sorry, I gotta use my other thing here. Let's crank into B. Love me the perps. All right, so now we need to calculate the wavelength associated with an electron moving at 68. Okay, and there's the mass. Okay, so for this one, so for B, it's going to be the same exact equation where wavelength is Planck's constant divided by mass times velocity, and a 6.62 e to the minus 34. Gosh, I wish I could remember anything. Now the mass of an electron, 9.1094 e to the minus 31, and the speed is going to be the same, 68 meters per second. So we both know that like electrons are going way faster than that. But here we're just looking at the relative wavelengths here, okay? So I'm going to pause you again. I'll do some math. I'll be right back. Okay, so here I end up with 1.0687 whatever e to the minus, damn it, that's a big minus, e to the minus 5 meters. So significantly larger. Is that small? Woo-hoo, that's teeny. But still, significantly like smaller. Significantly bigger. Like what we're getting here, this is a like unimaginably huge number compared to this. Like these two things, like they don't, like these don't even occupy the same universe, man. Like those are so different. Yes, I mean like the size difference is just ridiculous. So that's how that works. And I want you to clue into this, right? So this is the wavelength, 1 times 10 to the minus 5 meters. That's like actually, you see that with your naked eye probably. This wavelength of an electron. That's 68 meters per second, so that's not exactly great. So this is how this is something, oops, hold on, let me see if I can get this here. I want you to clue into that so we can see how an electron microscope works. So this is a piece of wood visualized from an electron microscope. Now, it's usually just black and white, and we colorize it because, you know, we're fancy like that. Basically, what happens is the wavelength of light gets to be too big for measuring some of these things, right? Like it's like a physical object like this. So if the wavelength of light is just too big, it can't quite get like the detail out of this. So what people have realized, these really smart people, is that if light is not, if light can't give us a clear enough picture because the wavelength is just too big, well, why not use something with a much smaller wavelength, like an electron? Right? Because electrons are physical objects, and we can control the wavelength of that electron based on how fast it's moving, right? Right? Because like if you remember the wavelength, Planck's constant, that's locked. The mass of the electron, that's locked. But if you mess with the velocity of an electron, you can change its wavelength, man. And the way you can change the velocity of an electron is by putting it in an electric field of varying strength. So the greater the electric field, I mean, just like basically, if you think of it, a bigger battery, huge battery, those electrons go flying in a vacuum. A much smaller electric field, they don't go quite as fast. So you can tweak the wavelength, and you can focus electrons, right? Because they're able that you can make the wavelength so small that they can wiggle into these little tiny details right down in there. Look how small that is. Like they can wiggle into those little tiny details of, like, you know, the space between like the cells of a piece of wood. And that's how an electron microscope works. We can get really, really fine detail because we can tweak the wavelengths of the electrons, which is like unbelievable. Like, I mean, we can like watch molecules happen because of like tweaking the wavelength of electrons, which is, in my opinion, just crazy. Also, crazy. You people not doing any of your work. I know it's beautiful outside. I know it's the end of the year, and I know it's all online stuff. But tough luck, man. This sucks. It sucks for everybody. And one of the things you got to learn how to do is do your work without somebody like daily looking at you in your face and saying, "Oh, you're gonna get your work done." This is like dress rehearsal for what's coming at you next September. No one's going to follow up with you. No one's going to be babysitting you. They will let you fail, and they'll still take all of the thousands of dollars. So what you need to do is outline 7.4 and do 36 to 42 in your book, and you need to do it on time. That's all you got to do. Still love you guys. We'll see you. Bye-bye.